Okay, so welcome to the second part of this talk. So now we are going to discuss Giordani module attached to an abelian variety. And so we start with an abelian variety A. So again, I'm going to let K be a finite field. Of size Q equal P to the N. And then so A over K is an abelian variety. An abelian variety of dimension G. And so as we saw in the previous, so this means that if we look at the P divisible group, this has height 2G. Okay, and as we saw, this is basically the inductive limit on the P to the N torsion point of our variety. And I guess you can think of this as the big union of all the P to the N torsion point. Okay, so we're going to call this, we're going to be calling, as you said, G, just to shorten the notation for this group. And then, so what we have is that, so as we saw earlier, the Giordani module, Mg, by construction, this is the inductive limit of the Giordani module of each finite module, and we get this. And we saw that there is a connection between this and the Tate module. So yeah. Yeah, so yeah, so this is the Giordani module for G, and this Giordani module is related to the Tate module. So from now on, what we are going to do, we are going to call this TP to the G. It would be the same as, this would be the same as our Tate module of G. Okay. Right, so as the last remark that I made is that the rank of this module, if you remember the functoriality statement, says that the rank of the modules, so the length of the module is the rank of the group or the height of the group, and so clearly you see that the size of this module is the same as that of the Tate module we saw in previous session, and so then you have this identity. Okay, so the first theorem that we are going to prove is basically it's the Tate isogeny theorem for P equal L. So that's what we're going to prove now. So the setup is that we let A be abelian variety. So these are abelian varieties over K, our base field. And then, so the theorem says that, so the map, so if we tensor ZP, with AB, and then we map these to over dk TPB TPA is an injective map. It's injective. And it is an isomorphism when K is finite. Okay. So we are going to prove the theorem, and basically the injectivity is proved in the same way we did for L different from P. So you can prove this by mimicking the proof in the case when we had L not equal to P. So it's essentially the same thing. So we only have to prove surjectivity. Okay, so that's the main thing we have to do, and we are going to do some preparation in order to be able to do this. And the first thing that I want to observe is that, again, we can reduce this to, can reduce the proof to the case when A is case simple. And we do this by using the same kind of argument So this would be using the same kind of argument as in the case L different from P. So it means that in that case, it means that we only need to prove that. So what we need to prove is the following. So when A is case simple, then if we take QL and then we tensor over Z with the endomorphism ring of okay, this is and we look at the map that goes into DK of the third module. So all we have to do that this is surjective. Okay. So this would be the only part that is new in what we're going to prove. And in order to prove that, we are going to start with a lemma. So the lemma says the following. So we let G be an irreducible polynomial in coefficient, sorry, not irreducible, just a polynomial with coefficient in the field of fraction of the Witt vector module, a Witt vector ring. So if you assume that this is a monic polynomial, so we want to assume that this is non-zero. Going to call degree of G is equal to D positive. And then now we are going to let M be the module we get by quotienting so we let didn't think I'll have a hard time writing bold-face D, but this is the bold-face D. And then we quotient by bold-face D time the. So we look at the. So we are looking at the left ideal generated by G, and then we quotient the ring by that ideal. So this gives us a left module. And then the statement says that then M is a left DK module of specific DK over one module of dimension D as a K0 vector space. So if you look at this statement, it's the analog of the what you see the first time you encounter a number field. So you take a polynomial and then you quotient the ring of polynomial with rational coefficient by that polynomial, and you say that it's a number field, meaning it's a vector space of dimension of finite dimension over Q. So it's exactly the same case here, except that we are in the non-commutative setting. And so what I'm going to do, just convince you that that's the case. So so basically what we do, working as in the commutative case, we can show the following. So what we show is that if I take a polynomial with coefficient in dk, we can show that a polynomial like this, there is a unique representation where you can write h as, so it will be alpha time the polynomial g of x, and then you have c0 plus c1 of f plus c d minus 1 f to the d minus 1. And in this case, alpha would be an element in the Dieudonné ring, and then the ci would be element in the field of fraction of the Witt vector. The ring of, the fraction field of the ring of Witt vector. And so what that means is, so this means that, this means that M is finite dimensional as a K0 vector space. Yeah, so that's what it means. And so we are going to use this lemma. It's a very simple lemma, but it's very crucial. And I'm going to, in order for us to use the lemma, I'm going to complement it with an exercise that I'm leaving to you guys. So the exercise says the following. Show that if you take a subset of the Dieudonné ring, then this subset is a two-sided ideal. If and only if there is a polynomial h of x with coefficient in QP of x such that meaning that our ideal is two-sided, so it means that we can write it as a GK module on the left, which in this case would be generated by h of x, and it would also be generated on the right by the same polynomial, and I'm going to write this as a shorthand like this. Sorry, I knew I was going to do this mistake. So this would be, that's, I'm glad I caught it early. Okay, so this is a key fact. So it would be generated by this. So h of f to the n, Okay. So in other words, what I'm saying that any two-sided ideal in the Dieudonné ring will be generated by a central element. So that's the content of the exercise. And using that exercise, we are going to prove this lemma, or I guess one could even call it a theorem, because it's quite important, actually. So it says, the lemma says the following. So let Gx be irreducible of degree m such that the field generated by G, which I'm going to call E, So if we take the field generated by G, then this is a subfield of the fraction field of the ring of Witt vectors, and then we let pi in E be a root of G, and we let R be n divided by m, and we are going to fix a generator of the Galois group of K0. So sigma lifts the arithmetic Frobenius. Okay. So under this condition, the lemma says the following. Then, so there's still one more thing to say. Let delta be this quotient. So you take this quotiented by so then the lemma says that delta is a cyclic E algebra, and it's which is isomorphic to this cyclic algebra. So don't worry if you don't know what this notation means, because we are going to define it in the course of the proof. So the cyclic algebra given by K0 over E, the element sigma to the R and pi. So that's the content of the lemma. And the proof is really very beautiful. So let's do it. Okay. So recall, the first thing I want you to recall is that the degree of, so recall that so the degree of K0, which as I said few times is the field of fraction of the Witt vector ring, the degree is n, right? So this means that if you look at the center, of delta of this quotient, so the center of this ring is simply the algebra, the QP algebra generated by f to the n. Okay. And what that means is, so it means that, so this means that when we take delta, which is by definition, the quotient of this algebra by the ideal G generated by this polynomial is is an algebra over this ring. So I'm going to call I'm going to call this Z. It's an algebra over Z, which is in this case QP f to the n modulo G f to the n. Okay. Now, what is this algebra? We are going to. Now we observe that. So we can rewrite Z, right? So I'm going to so Z, as we just saw, this would be f to the n quotiented by G f to the n. And we can rewrite this. So what I'm doing here is basically kind of redundant. If I can write this f to the r m, and then I can quotient this by G f to the r m, the ideal generated by G. And then I can rewrite this as QP f prime to the m mod out by G f prime to the m, where I set f prime to be equal to f to the r, right? So we can do this. And then when we do this, then we see that now we see that the map that goes from, will go from E to Z. I'm going to repeat f prime to the m So this map, we send pi, which is a root of the defining polynomial, to f prime to the m. And when we do this, this map is an isomorphism. And of course, so this isomorphism, so this makes delta into an E algebra. And not only it's an E algebra, it's even cyclic, and it is even cyclic since we have the relation. So what relation do we have? So these are relations that so the first relation is the one we just wrote. So we know that pi, if we take f prime and we raise this to the power m, it will be this, and then when we take f prime and then we multiply it by x, then this is going to be sigma to the r x times f prime, and this is going to be true for all x prime and k0, right? So by construction, these are the relations that we have, and so this conclude, and so this is what the definition of a cyclic algebra is that you give a set of generators and then you give a relation. So the saying that it's cyclic means that one of those generator is the action is given by by a cyclic extension. So delta is a cyclic algebra, and that proves the lemma. Right. So it's a very beautiful lemma, and we are going to use it to prove our next result, which is basically the key result we need to prove the first theorem that we saw. So the next theorem is the following. So we let H cube P of X be monic, irreducible, of degree n, with non-zero constant, and then we let L be the field generated by that polynomial. So QPX quotiented by H, and define T prime to be the algebra that we get by quotienting the Dieudonné ring. And then the theorem says that n D prime is a central simple L algebra. Okay. So we basically did most of the hard work already. So the lemma, this lemma really simplified the proof. And we are going to keep the notation in the lemma. So the first thing is that I'm going to let E be the intersection of the field of fraction of the ring of Witt vector with the field L generated by our polynomial H. And so we let this, and then we denote by G the minimal polynomial So this is the minimal polynomial of E. Okay. So now we're going to set. So M would be the degree of G. And then R would be N divided by M. And so basically, once we do this, then we can apply the lemma to what we just, to this setup. So now recall that G prime by construction is basically is this quotiented by h of f to the n, right, which is the same as taking k0 of f quotiented by g f to the n. Okay. And so the center, so if you look at the center of this algebra, which is, if we call it z of d prime, then the center in that case would be qp f to the n quotiented by, oops, sorry, this should be h, quotiented by, okay, I'm mixing up my notation, quotiented by h to the n, right? And this is isomorphic it's isomorphic to the field L, which, if you remember, it's qp of x divided by, right? So by the same kind of argument we did earlier, it's isomorphic to this field. So at least we know that. So this means that, oops. So this means that we know that D prime is a central algebra, is it's a central algebra over L. Okay, so that gives us essentially the first part, so central, and now we need to show that it's simple. And now the second part uses the exercise that we proved earlier. So by using this exercise, we know that since the polynomial is irreducible, since this polynomial is irreducible, we know that d prime must be simple, right? Because if it's not simple, then you will have a two-sided ideal, and the quotient by that two-sided ideal will give us a smaller algebra, and that smaller algebra will be given by a polynomial which necessarily divides h, and this will contradict the irreducibility of h. So this gives us that D is simple, but we can say a bit more, right? So by construction, we know that the field E is contained in L, and so by the lemma, so I'm going to say by the lemma above, we know that delta 0, which is K0 over E, sigma R and pi, is a cyclic E algebra contained in D prime. right? E is contained in D prime, the generator. So if you look at by construction, this algebra is contained in D prime. And now the key fact that we need here is that L over E is, I guess you could say, is ramified, or even totally ramified. Is by construction, E is the maximal and ramified sub-extension of K0, which is contained in L. So what this means is that it means that L cannot split delta 0. And so it means that if I let delta be the base change, if I take delta 0, and then I base change this via E, I base change this via E to L, is still a cyclic algebra. It's a cyclic algebra which is contained in D prime. So, but in this case, it's a cyclic L algebra. And in fact, delta is simply obtained by, so you take the composite term of K0 with L over L, sigma R and pi. So that's how you get the base change of delta, the base change. And so this is a cyclic algebra which is contained in D prime. And now you can conclude that by Wedderburn, so by Wedderburn theorem, we know that G prime will be isomorphic to MR delta. And this proves the result that we want. So this is the key theorem that we need in order to prove the third theorem for L equal P. So now let's state a corollary of this theorem. The corollary of the theorem is the following. So if we let H be irreducible, I guess monic, such that it has non-zero constant term, and then you let L be this field, the field generated by H, and let G prime, so basically the same notation as above. So we let this be the algebra generated by H, and M a finite D module a finite left D prime module then the the corollary says the following, then we have the following dimension agree. So if you take the dimension over K0 of the endomorphism ring over K0 of Fn of M, then this would be the same as taking the dimension over Qp of the endomorphism ring over D prime of M. Okay. So we did the hard work already. So let prove the. I'm going to give you the main ideas of the proof and leave the rest to you, since we already did 2 proofs in this lecture. that's more than enough. So the first thing is that so since D prime is simple, so we only need to prove the. So we only need to prove the corollary for a simple module, for M simple. Okay. And so now, if M is simple, for M simple, then what do we know? Right? So what is, you see the commutant, which we saw. So the commutant of M, in this case, it would be C. And if you remember, it's exactly the member on the left of the right of the equality that we want to prove, right? And the bicommutant in that case would be D prime itself, because we are in the same, so it's the endomorphism ring of our module over the commutant. And then we recover our simple ring, right? And now the key thing that we need in order to complete the proof is the following. So now observe that so we want to observe the following fact. So the first one is that this is something that we already use. So this is K0 of F, 1 over F, which is just K0 of F, right? And then its center, so the center of our module we already saw this. So the center is given by, right? And basically, if you look at K0 of F to the N, divided by H of F to the N, this is the maximal commutative L algebra contained in D prime. And so if you put all those things together, this there will, so therefore the equality follows from properties of simple, or you could say semi-simple modules. Okay. So most of these results, if you know them, it's really, really easy to prove them using some of the preparation that we did. So these are the results that we need in order to prove the Tate isogeny theorem for P equal L. So now proof of main theorem. So remember, what we have left to prove is the surjectivity of the map we have. So in order to do this, we are going to let this the endomorphism ring. Sorry, the endomorphism algebra of our Abelian variety. And so we know that the center of D is the field generated by the Frobenius. The Frobenius endomorphism. I'm going to drop the superscript A. Okay. And what we know is that by functoriality, if you look at the way the Frobenius endomorphism act on the Tate module, it would be the same as the nth power of F. Right? And so what that means is that for our main theorem, it would be enough to prove this, that we have this dimension equal. So we want the dimension over K0. We take QP tensor with the endomorphism algebra of A. So in this case, we're going to look at the P divisible group. And we want to prove that this is the same, taking the dimension over K0 of the endomorphism. So basically what we are doing is we take the equality that we started with and we tensor it with QP. So the reason why we put the opposite, we take the opposite is simply because we have the Giordani functor is contravariant. So, but if we can prove that these two members have the same equality, then we are done. Okay, so now all we have to do is prove this. So now the first thing that we want to observe is that the action of So if you look at the action of VP pi and Z, which is the center, sorry, so the action of VP and not the center, but the action of the decay module, this action commute. And they commute for the simple reason that pi is in the center. Pi belongs to the center of, which has been said quite a few times, generated by f to the n. Right, so these two actions commute, and so we will make use of. So that's the first observation that we make. We are going to use this observation. And now recall that, so if we let FA, the minimal polynomial of Frobenius, sorry, the characteristic polynomial, so this characteristic polynomial, as we saw many times, is the power of the minimal polynomial. So GA, the minimal polynomial. Okay. And not only that, we know that, and both of these are independent of so both are independent of L and P. I mean, when you view them as acting on the Tate module, they are independent. And so if we write so if we take QP and then we tensor it with our center, this would be the same as taking QP and then modding out by the ideal generated by the minimal polynomial, which of course we can write as so we can write this as a product on all the places dividing P, QP of X divided by the polynomial generated by GAV, where GAV is so before I write this, I want to say that we can write this decomposition, we can write its product on the V dividing P of ZV with obvious notation. So here, GAV, this would be the minimal polynomial so it's the minimal polynomial of ZV over QP, right? So now we basically have a decomposition of ZV over all the places that divide P. And there's a similar decomposition. So the group G will also decompose the same way. Remember, G is this P's visual group. It will also decompose accordingly. Meaning that I can write G as a product over all the places dividing V. GV, and GV is a P divisible group. Yeah. So the GP is the P divisible group, which corresponds to the idempotent of, so the idempotent of ZV. So you have a ring that we write into a product of rings. So each of those factors correspond to an idempotent, and this idempotent would give us a factor which is a P divisible group over K, right? Okay, and we also have, so this means that if we take the Tate module, so the Tate module is also going to decompose into a direct sum of the places, and now the Tate module of GV. So each of those, all of these decomposition are compatible with each other, right? And now the key fact is that so we see that, right, if we take GAV of F to the N, this is an element of our algebra. And how does this act on the local factor GV? It acts through the evaluation of our polynomial at the Frobenius. But remember, GV is the minimal polynomial of Frobenius over ZV. So if you make this evaluation, this will be 0. And so what that means is that it means that the action of our ring on this module is through the following quotient. So it means that VP of GV is a left module over the quotient. So this quotient is dV, and dV is simply our Giordano ring quotiented by GAV Fn. Right. So each of those polynomials determine a local factor of the algebra, and the Frobenius on that factor act through the quotient by that algebra. And then everything about this decomposition is nice. So it means that we get that this decomposition are compatible with the isomorphism that we started with. And so we see that So we see that these decomposition are compatible. So what are these decomposition? The first one is that if I take the left-hand side of the equality that I want to prove, this will be isomorphic to the product on all the V dividing P. And now I'm taking the endomorphism ring Fn of the Tate modulo of GV. So that's the first decomposition. And the second decomposition is the one on the right-hand side of the equality. So if I take this, and then I look at then this will decompose as the product over all the V dividing P of the endomorphism over dV of Vp of GV, right? So from this, you see that, so it is enough. So these decomposition are compatible. So what that means is it is enough so it is enough to show that if I take the dimension, so basically I compare the factor one place at a time. So it means that if I can show that the dimension of GV, the dimension of the Tate module at V over K0 Fn is equal to the dimension over QP of this endomorphism ring. And if I can prove this for all V, then I'll be done, right? And now the good thing is that this follows from the corollary we just proved. Okay, so we just proved that we have this equality of vector space, and if you trace this back, then you will see that it means that the vector space that we started with have the same dimension, hence the map that we construct must be an isomorph. It must be surjective, hence it's an isomorphism. Okay. So that's a fun part, and so now the thing that we have to do, we need to write down the local invariant of the. We want to write down the local invariant of our algebra and of endomorphism ring, because that would be the key element in proving the under-Tate theorem in the final lecture series. So now we want to discuss the local invariant for Abelian varieties. Okay. So again, the setup is what we had before. So K is a finite field. A over K is an Abelian variety. And so we let D be the endomorphism ring, the endomorphism algebra of A. And if you remember, the first thing we saw was the Albert classification. So it says that D is it's a totally definite division algebra. Right, and the center which we are going to let D is just the sub-algebra generated by the Frobenius. Okay. And now I'm going to write the decomposition that. So remember, we had those decomposition that we just proved, and so in the proof of the theorem we saw this decomposition that. So keeping the notation. We have this decomposition. So we know that dV, which is the endomorphism ring, of this P divisible group is the same as the endomorphism ring of this state module. The opposite, because we are dealing with a functor which is contravariant. And now basically we want to, the goal is here, we want to compute the invariant of dV, because that invariant will be crucial when we try to, this invariant will be crucial when we try to compute the Abelian variety in the bijection given by undated theorem, right? And now the decomposition that we saw, which we wrote above, so recall that we know that dV by construction is equal to this. Okay, so I'm just rewriting the notation. I'm just rewriting a decomposition in the previous section that we did. Right? And so we want to compute this local invariant, and the good thing is that we the good thing is that we know what this is. So by the theorem that we saw, so if we look at one of the main theorem that we prove, we know that So we know that the invariant of dv, so let me write this on a separate line. So we want the invariant at v of d, and this would be the invariant of dv, and we want this in the Brouwer group of this field. Okay. And this is the same that we saw. This is the invariant of the following cyclic algebra, because those are the calculations that we did for the cyclic algebra. And what was that cyclic algebra? It's delta V. And so delta V was, we take the compositum of K0 with ZV over ZV. This is sigma prime. And this is pi to the FV divided by GV. And I'm going to say what these notations are. And here, FV is the degree of the residue field. The degree of the residue field of ZV. And of course, GV is the GCD of FV and N, right? And so given that, and of course sigma prime in this case is just sigma to the R, where R in this case is N divided by FV. Okay. So if you go back and look at the proof that we did, then this is what you're going to get from that discussion. And so that tell you that you can write the invariant of your quaternion algebra very easily. So if you put that together, so we get that. If we take the invariant of D, it would simply be the valuation of the Frobenius at pi divided by the valuation of Q times the degree of the local field. And then this is, you want to see what this is Q bar, and this is the invariant of our quaternion algebra. And so clearly this is something that we can compute very easily. And we are going to use this invariant in the final lecture in the proof of the undated theorem. So I think this is a good place to stop for today. Thank you and have a good weekend.